The most astonishing fact about black holes is that they don't require matter to be squeezed into existence. They can actually form in a region where nothing exists. Textbooks have long told us that a massive star, unable to support its own gravity, collapses under its own weight, giving rise to a black hole. Matter is seen as the necessary ingredient, and gravity is the tool that drives this process. However, in the energy filament theory, the fundamental concept is not simply matter plus gravity. Instead, it is a vast, ever-changing ocean of energy that can stretch, twist, and tear apart in dramatic ways. In this theory, gravity is not the core principle driving the formation of a black hole. Instead, gravity is merely a consequence of the energy C being stretched into what we call a curvature slope. This radically alters our understanding of black hole formation. And according to the energy filament theory, there are three distinct ways black holes can come into being. The first way is the traditional textbook explanation, mate-induced curvature collapse. A huge amount of matter pulls the same patch of energy C tighter and deeper, and once the star's structure fails, the curvature slope becomes so steep that it essentially becomes a vertical drop. The core gets dragged into the pot of soup, while the outer layers naturally split off into the crushing band, piston layer, and outer critical layer. These form a four-layer structure, locking everything into place during the collapse. This is the typical stellar collapse black hole. The second, more unexpected pathway involves the energy C itself collapsing, without the need for any matter. Imagine a pot of incredibly thick soup. When you stir it forcefully, the center suddenly forms a deep whirlpool. This same phenomenon can occur with black holes. The energy C is violently sheared, twisted, and stretched until one region of it reaches the maximum curvature limit, causing it to snap and instantly form a black hole. In this case, no star is required, just the raw dynamics of the energy C itself. The third way a black hole forms is through average gravitational collapse, which was more prevalent in the early universe. The collapse is triggered by the gravitational influence of many unstable particles, which then collapsed into a primordial black hole. This particular method is the origin of primordial black holes. We'll dive deeper into this fascinating topic in the next episode. The overarching conclusion is that black holes are not defined by matter, as is commonly believed, but by curvature. As long as the energy C is stretched to a critical point, it would collapse and form a black hole, regardless of the presence of matter. The collapse of a star is just one of many possible outcomes. The true essence of a black hole lies in the energy C transitioning into a new state of structure. When the four layers come together and the core begins to churn, a black hole is formed. In the next episode, we'll explore the intriguing nature of primordial black holes, the first black holes to form in the universe when it was still in its early, boiling stages. Be sure to follow and share as we continue this groundbreaking journey with a series of new physics insights that will help you understand the universe like never before.